Hello friends, welcome to the fourth segment of Thermodynamics of Polymeric System under the edges of Polymer Process Engineering. Now in the previous lectures we covered about the activity coefficient models. We discussed about the Flory-Huggins theory because we were discussing about the different thermodynamic model. Those can predict the behavior of polymeric system. We discussed about the Hansen solubility parameters, developed the correlation for solvent activity. We discussed about the group contribution model and discussed about the equation of state model. In this particular segment, we are going to discuss the statistical associating fluid theory, that is called SAFT, and then we will discuss about the SAFT application, and we will discuss about the Vera equation of state. Now let us talk about the statistical associating fluid theory. The thermodynamic perturbation theory, which is given by various workers, they serve the foundation of statistical associating fluid theory. This is developed by Chapman and co-workers. There have been several numerous publications in this SAFT theory. It originally emerged, and Muller and Gubbins they have examined the various SAFT variants and how they are used. Now, for polymeric solutions, the SAFT version of Hong and Rad's is used most widely. The PC-SAFT, that is perturbed chain SAFT, a promising novel variation of SAFT for polymer solution. This was put by the Gross and Sadowski in 2000. Now, we shall limit our discussion because this is the latest one. So, we shall limit our discussion to these two SAFT versions in this particular instance. Now, both the equation of state, these can be expressed as distinct contribution to the molar Helmholtz energy because the fundamental components are equal. The difference between the system's molar Helmholtz energy and its molar Helmholtz energy in ideal gas state under the same temperature, pressure and composition is known as the molar residual Helmholtz energy, and which is represented as A residual. Now, it is calculated as the sum of contribution of hard chain terms AHC, this is referred as AHC, and a dispersion term A dispersion, and the associated term or association term A association. So, this can be represented as A minus AHC plus A dispersion plus A. Now, using the common thermodynamic relationship, that is A is equal to summation NIA, the pressure and the chemical potential can be calculated from the expression which we are going to write. P is equal to minus del A over del V at constant temperature and N, and mu I, that is the chemical potential, del A over del Ni Vt. Now, the SAFT and PC-SAFT, that is hard chain term, this a chain in the molecular model underlying the SAFT is made up of two hard sphere segments. The covalent bond hold these portion of hard sphere together, and both SAFT version hard sphere term is the result of two contributions. Now, the statistical associating fluid theory, it is the combination of a hard sphere contribution and a term due the conductivity of these hard sphere segment, which is given by AHC over RT. This is equal to MAHS over RT plus A over RT. M is equal to psi Mi, where M is the average chain length of molecule in the mixture. The hard sphere contribution AHS is shown by the Boblink and Mansouri, this hard sphere equation of state for mixture of hard sphere. Now, this can be represented as AHS over RT 6 pi rho 2, 1, where psi 2 square over 1 minus to the whole power 2 plus xi at the initial, then ln 1 minus. This can be given by k is equal to pi over 6 rho summation of xi mi dii to the power k. Now this k can be pi is equal to 6 pi over 6 rho summation xi mi dii k, where rho is the number density and dii is the temperature dependent hard sphere diameter. Now this is the temperature dependent hard sphere dii obtained from the equation dii t is equal to small theta I 1 minus 0.12 e to the power 3 epsilon I over kt, where this mi is the hard sphere diameter and theta I is the energy parameter and epsilon I is the pure component parameter. Now the chain term, this A chain is given by A chain is given by RT is equal to summation xi 1 minus mi ln g to the power hs, where this term is so called hard sphere radial distribution function at close contact. Now this g ij hs is equal to 1 over 1 minus d di dj over di plus dj plus di dj over di plus dj square 3 1 minus. Now the Hong and Redo's version of this SAFT chain, SAFT, the chain etc. at all, the dispersion term is used, and this term is given by A dispersion over RT is equal to summation I from 1 to 4 j is equal to 1 to 9 dij ukt to the I tau j, where tau is a constant equal to 0.74048. Now for mixture, the van der Waal one fluid mixing rule or the volume fraction of the mixing can be used, and the van der Waal mixing rules are given by this particular equation u over kt is equal to summation I and j xi xj uij kt dij over xi xj dij3. Now here kij is the adjustable binary interaction parameter and dii is the hard sphere diameter. So dij is equal to di plus dj over 2. Now in SAFT dispersion term represents the interaction between the individual segment, but PC-SAFT, the dispersion term represents the interaction of chains of segment. So the expression A dispersion derived by the Gross et al., and this is the equation is given by A dispersion over RT is equal to A1 over RT plus A2 over RT. Now, this term on the right hand side of the previous equation, they are defined by the equation like A dispersion RT is equal to A1 over RT plus A2 over RT. Now, A1 over RT is equal to minus 2 pi rho m square u kt, then I is equal to 0, 6 AI m ni. Now, A2 is over RT is equal to minus pi m 1 plus m 8 neta minus 2 square over 1 minus eta to the power 4 plus 1 minus m into 20 neta minus 27 neta square plus 12 neta cube minus 10 2 neta to the power 4 over 1 minus 2 minus neta square m square u over kt small theta cube. I is summation I from 0 to 6 bi m ni. Now, the parameter ai and bi are dependent on ai m is equal to a plus m minus 1 over m a1 I plus m minus 1 m minus 2 a2i, and similarly bi plus m minus 1 b1i plus m minus 1 m minus 2 b2i. Now, the reduced fluid density neta is defined by the equation which is given by the as per the following notation. Neta is equal to pi n, this is Avogadro's number, over 6 rho m dq. Now, both this SAFT and PC-SAFT contains pure component parameters, that is the energy parameter epsilon or u, the hard sphere diameter small theta or hard sphere volume v II, and the number of segments m per volume. For small solvent molecules, these parameters are obtained from a fit of vapor pressure data and a saturated liquid volume data. Now, for pure component polymer parameters, they are acquired from a fit to PVT data of a molten polymer and a binary phase equilibrium data, because polymer cannot be fitted because they are having the lack of vapor pressure. For the description of a mixture, one needs one binary interaction parameters Kij per binary, which has to be fitted to a phase equilibrium data. Now, if necessary, this Kij can be made temperature dependent, and in general the phase equilibrium are very sensitive to the Kij value. Now, here this particular figure shows the isothermal cloud point curve of HDPE and ethylene system, and here you see that this is a SAFT model. Now, if we go to the other things like Sanchez-Lacombe model, this particular curve shows the isothermal cloud point for HDPE plus ethylene system. Now, in this particular graph, the experimental results from the system of ethylene plus HDPE, they are compared with the modeling result using SAFT and Sanchez-Lacombe model. In both cases, Kij is taken to be linearly dependent on temperature, and due to the polydispersity of the polymer, the cloud point curve shows a dip in which a critical point is located. Now, if in the modeling of the polymer, it's assumed to be monodisperse, this behavior we cannot reproduce. The graphical demonstration of the previous figure, this demonstrates that although the deviation they are bigger at high and low polymer concentration, both SAFT and Sanchez-Locambé model adequately describe the experimental phase behavior. And the same system, this was modeled by Tumakaka using the SAFT and PC-SAFT model. Let us talk about the other equation of state. The equation of state based on the lattice hole theory. This is theory and created by Panayiotou and Vera in 1982. This was comparable to the Sanchez and Locambé equation of state. The first major difference between the two theories is that the Vera theory, the volume of a lattice site is arbitrarily fixed to be equal to 9.75 into 10 to the power minus 3 meter cube per kilomole. But in the Sanchez-Locambé theory, the volume of a lattice site is a variable quantity regressed from the experimental data. Now, fixing the volume of the lattice site, this eliminates the need for a mixing rule for lattice site for mixture. Now, the issue of having the various lattice volume for the mixture and the pure component, this is resolved by using fixed lattice volume. The volume should be chosen so that the lattice site and the smaller group of interest have nearly the same volume. Now, Vera et al. They choose the value of 9.75 into 10 to the power minus 3 meter cube per kilomole, which accurately reproduce the pressure, volume, temperature data for polyethylene. So, all these things are case sensitive. Polyethylene, polypropylene, all these things are case sensitive. The Sanchez-Locambé theory and the Vera theory, they differ significantly in two more ways. The Sanchez-Locambé believed that a random mixing combinatorial was sufficient to represent the fluid for both component and the mixture, and Vera created the equation that accounts for non-random mixing brought on by the interaction energies between molecules. So, this Vera equation of state in reduced variable, this can be represented as P reduced over T1, that is ln equal ln V1 reduced over V1 reduced minus 1 plus Z over 2 ln V1 reduced plus Q1 over R1 minus 1 over V1 reduced minus theta 1 over T1 reduced. Now, theta is the surface area fraction, V is the reference volume, and T is the reference temperature. Now, for modeling of the phase behavior of copolymer solvent system, the copolymer can be treated as a homopolymer with effective pure component parameters. McHugh and colleagues, they provided examples for this particular strategy. The drawback of this strategy is that the characteristics of a pure component polymer depend on nature and makeup of the copolymer. From binary polymer solvent phase equilibrium data, pure component polymer properties are usually derived. Now, it is feasible to describe the phase behavior of the same polymer in a different solvent using these parameters. The Redos and the co-workers, they use the copolymer, the SAFT methodology, in which the copolymer characteristics, they are computed based on solely the copolymer's molecular weight and structure, and it is found to be the superior method. Now, there are three binary interaction parameters for AB type of copolymer. The parameter governing the interaction between A segment and solvent molecule segment, and B segment and solvent molecule segment, and A and B segment interaction. So, the phase behavior of two homopolymer system can be used to determine the first two binary interaction parameter, while some copolymer solvent data must be fitted to determine the third binary interaction parameter. Now, once these parameters are known, predictions can be made for copolymer solvent system with the same type of copolymer but with a different copolymer composition. Now, in this particular figure, the constant temperature cloud point curves and PC-SAFT modeling of the polyethylene system with the different repeat units composition at 5 weight% of the graduation of the polymer. Now, the model correctly predicts the change in the location of the cloud point with changing co-monomer concentration in the polymer. Especially, it is interesting to see that ethylene and polyethylene system in the curve of the cloud point pressure as a function of ethylene ethyl alcohol concentration in the polymer shows this is the minimum. So, dear friends, in this particular segments, we discussed the different models for the prediction of a thermodynamic system, and for convenience we have enlisted couple of references. Thank you very much.